Hello, welcome to areas of parametrized surfaces and wormholes. So let's begin with a review of area. So let me go over this quickly since I'm sure you know a lot about area already. But it's a pretty ancient concept, and let's see where it starts. It starts with a little tiny unit square. So this is our unit of measurement, and what you do if you want to define the area of an object is you start stacking up these little tiny unit squares until you have a certain number of them. That will be the definition of your area. So I have this little triangle here, which of course you might remember some theorems from geometry that gives you alternative ways to compute. But again, I'm thinking of this as the definition of area. Literally, this is what you do. You just stack up these little blocks and then count up how many of them you have, or how many portions of them you have. Alright, so let's fast forward a couple thousand years from ancient times to calculus. And we have a planar region here given by, we have a top curve and a bottom curve. So let's call those f of x, y equals f of x, y equals g of x. G of x will be the bottom curve. Well, we can, using calculus, come up with the integral of f of x minus g of x. This computes the area for this planar region over the interval I, which I'm calling from a to b. Okay, so let's review why that's true. So if we think about that, well, what is the area? So this was kind of Riemann's great insight, where he cut this up into smaller regions. Okay, so others had maybe done this before less rigorously, like maybe Cavalieri, where you cut them up into these thin strips. And because these are rectangles, we can approximate the area very easily. So the area of one of these rectangles would be f at some point minus g at that same point. This would give you the height of, or the length of the rectangle. And then what we're going to do is multiply this times the base, which we'll call this delta x down here. Okay, this gives you one of them. Then what we do is we just add them all up. Okay, let's sum them up, however many we need. Okay, so depending on how good of an approximation we need, or how wiggly our curve is, maybe we can use 100, or maybe we use 1,000,000. It all depends on how accurate we want to be. Of course, in calculus, we want exactness, so we take it to the limit. We take the limit as these number of strips goes to infinity. They're going to get thinner. We're going to impose some restrictions that do this, and of course what we get is, once we do that, we are led to the definition of area using an integral. So this gives us an interesting direction into the concept of area, where if you have a fancy way to integrate, you can talk about the area of more interesting objects. But I'll leave that as just a remark, since we are interested in smooth things. So we're going to basically use the Riemann integral and ignore integration theory. So let's go to another case that you might remember. So let's talk next about the graph of a function. So we have a function of two variables, x and y, and it's a real valued function. So if it's a real valued function, I'm going to let a third variable, z, be the output. So you can think of it as the height above the plane. Two ways to visualize this. We have the domain, D, of inputs, and then we're seeing how these get mapped into the surface, which we imagine as some curvy thing. Alright, so using calculus again, we have a formula for the integral right here. So it's a double integral, and it's a little bit more complicated than the formula for area from before. However, let's go and review where this comes from. Okay, so it starts with thinking about vectors. So what I want to do is, if we're going to do area, we want to compare. So we want to compare a square in the flat plane. So we know how to do that using basic geometry. We want to compare that with a curvy, almost square-like piece of the surface. Okay, so it's like a curved version of it. So in some sense, the function f is telling us how to distort this square. So if we want to approximate the area on the surface, let me tell you the wrong way to do it first. So the wrong way to do it would be to take 4 points on our surface, let's say those 4, and then look at the plane passing through those 4 points. Certainly, intuitively, that feels like it's approximating the surface. However, you might find it surprising that there's some pathological examples where this area won't work. So in other words, triangulations might not be a good way to measure. So what we do instead is we look at the tangent vector. So I have the purple and orange vector visualized, and instead we think of this as a little piece of the tangent plane. All right, so if we have a little piece of the tangent plane, this is also going to approximate the curved surface, at least locally, and as long as this is a tiny, tiny parallelogram. All right, so instead of picking 4 points on the surface and looking at that plane, what we're going to do is we're going to look at a parallelogram spanned by those 2 vectors inside of the tangent plane. Okay, so that's the idea. And what we would like to compute is, well, what is this area and the area of the stretched out parallelogram? How do I compare those two? That's really what we'd like to know. Okay, so let's see what that looks like. So here's a larger version of that same picture where I have the purple vector and the orange vector. These are the tangent vectors, and let me remind you one way to write these vectors. Again, we're a little special here since we're in 3 dimensions and we have the special case of a 2 variable function. But here's how we can write it. So f of x with the arrow is the purple vector. We can write this as 1, 0, f of x. And f of y, we can write this as 0, 1, f of y, where with the subscripts I'm denoting partial differentiation. So the partial derivative with respect to x, partial derivative with respect to y. And again, if we have an area here, we'd like to know how we distort that with this map. So if you remember, the way we did this in calculus was this area of the parallelogram spanned by these vectors, you can compute it with the cross product. So if you have the cross product here, this will give you the area, and let's just do this super quick. So it's the length of the vector, and I'm going to use this ijk notation as a shortcut. 1, 0, partial derivative with respect to x, 0, 1, partial derivative with respect to y. All right, maybe it's a good point to pause the video, work this out yourself, and when you're ready, okay, you can hit play. We have negative fx, negative fy, 1. And we want to compute the norm of this vector. So this is going to give us, and I'm going to write them in a different order. Let's write this as 1 plus partial derivative of f squared plus the partial derivative of y squared. All of this under the square root. So this is telling me the area that I want to distort by. Okay, so one more thing to do here. Okay, so how does the area dx times dy change? Well, it's going to change by this factor. Okay, so how do I write that? Give me 1 second. How do I write that? We write it like this. So we're going to write the area on the surface. Let's say, let's not be too rigorous. Let's say it's approximately this number. 1 plus, actually no, let me write the shorter version. Let me just write fx arrow cross product fy arrow times dx times dy. Okay, so here was the area in the plane, and then I multiply it by this factor to compare them. See how the function f is stretching it. All right, now what I want to do is, hopefully you've seen this calculation before, what I want to do is I want to give you a reinterpretation of this calculation. So I'm going to change my notation slightly. Okay, so I have now a patch, so a smooth patch, let's say, And I'm going to have two variables, which I'm going to call u and v. And I have three coordinate functions that give me my description inside of R3. All right, so to do this, let's just study this cross product, but just with slightly different notation. And let's look at this in a new way. So let's compute this. Let me zoom in a bit. So I want to compute the cross product of xu cross xv and the square of this. So let me do it by first noticing that I'm going to write this as xu times xv. So this is the length of the vector xu times the length of the vector xv sine of theta. So this is a formula that I hope you remember from vector calculus. And then what I'm going to do is distribute the squares everywhere and also use the Pythagorean theorem. So anytime you're doing math with the Pythagorean theorem, I feel like you are doing something interesting. All right, so what do we get? We get xu squared, the length of xv squared, and then I'm going to write this as 1 minus cosine squared theta. Okay, and I even have this little reminder here. So if you remember, the dot product of a vector with itself is the length squared of the vector. So I am going to change this piece and make this look like xu dot xu, and I hope you forgive me, I'm not going to write the arrows for a while just to make this a little quicker. All right, so xu times xu times xu times xv dot xv, so these are dot products in R3, okay, minus, okay, we have to remember another formula for the dot product. Let me write it up here. If you remember, if you have a u dot v, two vectors, you can write this as the length of u times the length of v cosine theta, and that's exactly what I have if I distribute this and I have squares everywhere. So what I get is I get xu dot xv squared. Okay. So, all right, that's really all I wanted to show. So what? Why did I do this? So the reason is we can reinterpret this in a cool way as follows. This is, so namely the square of this vector, is equal to the determinant of a certain matrix, which let's write it as xu dot xu. Okay, and I need to multiply these two pieces. So if I multiply those two, that means I'm going to put xv dot xv in this corner. And then I have to do this, so xu dot xv, but then I have to square it. So one way I can write this is I can write it as xu dot xv and xv dot xu. Because remember the symmetry of the dot product, right? It's commutative. All right, so what we've noticed is that we have a chain of equal signs here where these are the same. So what we've proven is we've proven this interesting theorem where I'm going to write it like this. I'm going to prove it write it as xu, the partial derivative of the vector x with respect to u, cross xv is equal to the square root of the determinant of a matrix, which I'm going to call Gij. And now this gives us a new way to think about the area piece. So we could write it as the cross product, but now we have a different way to look at it where I'm going to define this new matrix here. And as mathematicians like to do, we want to make this brief. I'm just going to write it as Gij, square brackets. Okay, so basically it's the matrix of dot products of xu and xv. This leads us to a natural definition. So if we look at this matrix of vectors, okay, sorry, you might need to move my face. So if we look at the matrix of the dot product of the vectors xu and xv, that's what we're going to define to be the entries of this matrix, and this is just the regular dot product in R3. Okay, so one of the cool things, of consequences of this calculation is that if we have a quicker, easier way to check regularity. So computing the determinant of this and checking that that's not 0 is pretty straightforward. And this is a different way to check that x is regular. So it's actually, these are equivalent conditions. You can see why that's true. All right, so that's pretty neat. Now, why does the determinant show up? Let's talk about that next. So let's review a little bit about just linear transformations. Let's forget about smoothness and warping. Linear transformations basically stretch things in a very controlled way. So one of the things we can do is, if we look at the area of this little rectangle, we can write it as the cross product. And if you want the area of the image, t of u, so it's going to get maybe moved into this piece. And we want to write it as the product of the old area times something. What's that missing something? Well, this is the determinant of your linear transformation. So it's pretty natural to see this determinant pop up in area calculations. And you'll see this if you remember the change of variables formula as well. So this is going to lead us to finally our definition of a surface area. So let's start with a single patch. So in other words, our surface M is entirely built from one patch X. Okay, so that we can write it as M is equal to the image of an open set U. All right, so if we do that, then at this point we just do a victory lap over our definitions. We saw that a little piece of area should reasonably be given by this calculation. And jumping forward a bit, we know that we have a different way to express the norm of that cross product. That is exactly this square root of the determinant, which is what we saw last time. All right, so that will give us a pretty good definition of area. Let's go ahead and box this. So this is if we have step 1, which is a single patch. So we integrate over u, over the variables du, dv, and the square root of the determinant of this matrix Gij, which we gave earlier up here. All right, now a couple just quick remarks is that we need some extra pieces for this to work smoothly, pun intended. Okay, so what do we need? We need that, first of all, this matrix of partial derivatives exists, so at the very least C1, so that our derivatives exist and are continuous. We also want to make sure that this is a one-to-one on U. So what are we trying to avoid when we ask for something like one-to-one? We are trying to avoid something like this, where we have a parametrization, but a parametrization is always more than just the shape of the image, right? It's also how are you moving through space, right? So if you think of space curves, right, you can kind of move along the line forwards, then backwards, and forwards, and backwards. It's still maybe a line segment if you look at the image, but a parametrized curve will actually tell you, well, first you're moving forward, then you're coming backwards. So you want to avoid something like these folds, where it kind of folds back on itself. And of course, if you pull the sheet, then it would have bigger area than maybe what you intend. So one-to-one basically eliminates that. The other thing we want to make sure is, we did a cross product of two vectors. We want to make sure that that's not 0. So if you remember, making sure they're linearly independent will be enough to guarantee that. Another way to say that is that the rank of dx, the total differential, is rank 2. And the third way, as I mentioned earlier, is actually just computing the determinant of this Gij is another way to check this condition as well. So there we have it. Now what do we do if we don't have a single patch? Let's draw a quick little manifold where you can't write this as a single patch. So what do? Well, we just, hopefully our definition of this manifold M is that what we can do is we can just visualize it as the union of a bunch of patches of type 1. So here we want to write M as the union of patches. Let's write it as maybe X of UI, as in step 1, where step 1 is when it's just the image of a single patch. Alright, so I wrote it in this way, and you can see that these kind of look like little tiny cylinders if I visualize it correctly. And this will be our definition of surface area for just any surface covered by patches that satisfy certain conditions. So what do we want to make sure? Again, always issue is don't overlap. So if we're going to have more than one patch, make sure that they are of this form, where if they overlap, they just overlap in like a line or a curve. So those will have no area, so those will be fine. However, if you have two patches where you have this non-trivial overlap, this will not be okay. So you'll have to basically cut this up into 3 different patches or work a little harder. Alright, so this leads us to our definition. We're going to use the same formula, of course, with the understanding that, this might be a finite sum of these individual pieces where we sum over the UIs, but we have enough motivation to be convinced that under nice circumstances, this should be a good definition for surface area. Again, these are surfaces inside of R3. All right, a few quick remarks is that as long as our patch is C1, that's going to tell us that these GIJs, which remember are the partial derivatives of x with respect to the variables u and v, if we do dot products, that's still continuous. And if we do the determinant is a continuous function of a matrix, so that will remain continuous. And if you take the square root, also continuous operation. The only thing you have to avoid is, of course, taking the square root of 0. That's where you lose your regularity. But all of that is to say is that C1, that innocent little condition, is enough to say that this integral exists. Integrating a continuous function will exist as a Riemann integral. The other thing I want to mention is that this definition, for it to be a good definition, we want to make sure that it is what is called independent of parametrization. I'm sure I wrote it somewhere. It does not depend on the parametrization chosen. What do I mean by that? Without going into the full details, I want you to just refer to Block's book for that. Let's draw a picture of what we mean. So let's say we have 2 different pieces of the surface. So really what we're interested in, I'm going to call the surface S just this kind of curvy piece. It just so happens we have more of that. All right, so if we have that, what I have is I have 2 rectangles in the plane. Let's say this is U, and then I have another rectangle in the plane. Let's call this V, and we have parametrization. Let's call it Y arrow for our patch, and let's do this blue one will be X arrow for our patch of U onto what I want to call is this intersection. Let's call this the surface we're interested in, and this will be the overlap of XU intersected with Y of V. Alright, so what we have to check is if I use the notation where the GIJs is the matrix of partial derivatives, and if I do Gij tilde for the patch based off of Y, we need to check the following. We need to check that the double integral of x inverse of s, so this is actually defined over, let's say maybe this little corner. Okay, if we integrate that using the square root of the determinant of the GIJs, let's say du dv, this is going to give us the same answer as if we did the right side, which is the double integral, let's say, of y inverse of s. That is going to give us maybe integrating over this region over here, that upper corner. And if we do the square root of the determinant of gij tilde, since I'm using y here, and I don't know, let's call these maybe du tilde, dv tilde, just to be different variables. Okay, so we have to check that this formula is true. Let me just give you a tiny hint as to why it is true, of course. The hint is, okay, well, we want to consider a map from the plane U to the plane V. Okay, and let's call this maybe phi. So this is just a function from 2 space to 2 space. And what we're going to do is we're going to call this, let's do it maybe as y inverse composed with x. So if we look at this restricted to s, this seems to be the right map, where we start here, go to our surface S and R3, and then go backwards via y inverse. This will give me a function, and then you can check the change of variables formula. For such a map. Okay, and then see how that and the determinant of the GIJs, see how everything talks to itself. And the key insight is that the determinant of a composition is multiplicative. So you'll see how the formula really looks like a change of variables. Okay, but the calculations I'll just refer to you to Bloch's book.